Welcome back to Hypothesis Testing Part 2. We're going to take a look again more of what kind of goes on with a hypothesis test. We'll get into how to do one, step by step. But right now, what I want us to assume is we have this null hypothesis. Okay, and I'm going to be very specific. I'm going to take as our parameter of interest the mean, because that's what we've been working with. And let's say that I think the mean equals 13. My alternative is, I think the mean has decreased from 13. And we're going to test this because we're going to know what the sigma is. Let's say the sigma is 2, and our sample mean was 12.8. And our sample size was, let's say it was, I don't know, let's say it was 16. And we know the population was normal. That means I can clearly know exactly what our null hypothesis looks like. So our null hypothesis is the sampling distribution of the sample mean, and it's normally distributed because the parent distribution is normal. It's got a mean of 13 and a standard error of 2 divided by the square root of 16. So I can actually write this null hypothesis. It's got a mean here. One standard deviation away, and this null hypothesis is 13 plus 1 standard deviation away times what a standard error is, 2 divided by 4, which is just 0.5. It's a half. So times 0.5. So this is at 13.5. 2 standard deviations away is 13 plus 2 times what a standard deviation is, or 14. And 3 standard deviations away is 13 plus 3 times a half, or 14.5. So now I know what -1 standard deviation is away, -2, and -3 standard deviations away. And again, we got that by 13 minus 3 times 1.5, or 13 minus 1.5. 13 minus 2 times what a standard deviation is. Whoops, that's 0.5. And 13 minus 1 times 0.5. Just so that we're clear, 0.5. So if I took a sample, and I'm going to see where that sample mean, the sample is size 16, this mean is in this distribution. Is that normal or strange, or, does it seem that it shouldn't be in this distribution? Well, remember the significance level, and let's say that my significance level is 0.05. That means I only want to make a mistake 5% of the time. That means that 1.96 standard deviations away, this blackened area is where I'm going to make a mistake. In other words, if I got a sample in that blackened area, any sample mean in there, it's really in this distribution, but I'm going to reject the null hypothesis because I'm going to say that's so far out on the tail end, it's unusual. So that means I could make a mistake about 5% of the time, because really it could belong to this distribution. So if I really did have a sample mean out there and I rejected the null hypothesis, I would have made a mistake, right? But my mean here is 12.8. My sample mean is right here. And with that information, I would not reject the null hypothesis. The p-value for that is this pink area. That p-value is much greater than 0.05. And we could find out exactly what that p-value is. But just by looking at the picture, we're not going to reject the null hypothesis. Now, what if later on, however, we found out that the real distribution, that the mean really had change, but that just happened to be a really weird value in the real distribution. then we made a type 2 error if our distribution was this. If our distribution is black, we wouldn't reject the null hypothesis, so we didn't do anything wrong. And that's kind of what happens with a hypothesis test. So what we do is we call the black thing our probability of a type 1 error. Everything else here is called a type 2 error. In other words, if we didn't reject it and we should have, we would get the probability of a type 2 error. Don't really deal with that much in this class. But those are the ideas behind some of the problems that you'll see on a test. And you saw some on test 2. You'll see it again on the final exam. If my null hypothesis was that the mean was 25, the alternative was that the mean was less than 25. Later, I didn't reject. Based on my sample, I did not reject the null hypothesis. But later, somehow, some little miraculous thing happened. Later, I find the mean of the distribution really was 25. Then I didn't make an error. Okay? So that's one type of problem you could see. Now let's say that my null hypothesis was that the proportion is 0.35. But I believe that the proportion has increased from 35%. I reject the null hypothesis based on my sample. So you're not seeing the test done at all. You just know based on your sample, you rejected the null hypothesis, meaning that we think the mean has increased. But later, I find the sample proportion really was 0.35. That means I had said I had enough evidence that that was true, and it really wasn't. So that's a type 1 error. I rejected the null hypothesis when I shouldn't have. Now let's look at the third case. And that's the one that where I don't reject where I should have. So the null hypothesis is the mean of the differences is 0, because whenever we have a 2-sample problem in our class, we're just going to assume that the null hypothesis value is 0. The alternative is I think the mean of the differences is less than 0. That the before minus the after, the before value is less than the after value. And so I do not reject the null hypothesis. But later I find out mu sub d really it was less than 0. The before value was less than the after value. So if that's how I hooked up my differences. So this is where I make a type 2 error. So this is how hypothesis testing kind of underlying what's going on when we reject or do not reject. So with the hypothesis testing, the very first thing, and we've gone over this before, the very first thing you want to do is write the null and alternative hypothesis. Very, very important. H naught and HA, because it drives the test. And I would even go further to say state the null hypothesis. Write exactly what the null hypothesis is. Determine your alpha. What was stated in the problem, because in our class we'll always give you the alpha. And remember what alpha is. It's the significance level. And the significance level is just the probability of making a type 1 error. The triple line means it's a definition. Significance level can be defined as the probability of a type 1 error. And then number 3 is to calculate your test statistic. Calculating the test statistic, remember what the test statistic is. It's how many standard deviations our sample mean is. So the test statistic is how many standard deviations our sample mean is in the null hypothesis distribution. So that sample mean is really far out in the tail end. That is not a good thing for the null hypothesis. that's probably evidence to show that the null hypothesis can be rejected in favor of the alternative. That's the basic idea. And then step 4 is either you're going to do the p-value method or you're going to do the classical method for doing a hypothesis test. So you'll determine those two, and step 5 is based on the p-value or classical method, you're going to determine whether you reject the null hypothesis. And then the last step would be state the conclusion in the context of the question. So now it's time to do an actual example. Boys are known to have a mean weight of 85 pounds at a certain age. A claim was made that a certain children's home was underfeeding the boys. So a random sample of 25 boys this age was weighed. It produced a mean weight of 80.94 pounds. I'm going to put the pounds in there. The population weight is known to be normally distributed with a population standard deviation of 11.6. At a 0.05 significance level, test the claim made by this concerned citizen group. So number 1, what is this this claim? Well, it's believed that the weights of boys at this certain age is 85 pounds. This group believes that they're underfed. That implies that the weight they think will be less than 85 pounds. And we have this population standard deviation and sample size here, so we can actually completely state the null hypothesis. We know it's normally distributed because they said that the weights are usually normally distributed. It's got a mean of 85 and a standard error of 11.6 divided by the square root of 25, which is 2.32 for a standard error. Now part 2, what's the significance level? Well, they want us to do it at a significance level of 0.05 because it's a relatively serious matter. So what we need to do is how many standard deviation is this sample weight right here in this null hypothesis distribution? We know how to find that. We take that weight, we subtract it from 85 and divide it by the standard error, which is 2.32. We just figured that out. Now, generally, if this didn't come out perfect, I would just put this in the formula, 11.6 divided by the square root of 25, because I want to be as accurate as possible. So this is negative 1.75. Now, this is where our techniques between classical and p-value diverge. To find the p-value on a left-tailed test, it's the probability that our z is less than that test. We could get a z less than that test statistic. So the probability z is less than negative 1.75. And that's when you would take your standard normal table, you'd look up negative 1.75, and I get a p-value here of 0.0401. If I were doing the classical method, that means I have to find the critical value. In other words, that value such that on the number line, if my test statistic is further out in the tail end, I'm going to reject the null hypothesis. So my critical value here, since I'm in a left-tailed test, is going to be negative z.05. That's what it would look like if I was formally finding it. In other words, I'm trying to find, because this is a left-tailed test, I'm trying to find the z-value such that 0.05 is to the left of it. And I know that that z-value is negative 1.645. So my critical value is negative 1.645. Remember what this symbol means right here. It's always finding the value such that that's 0.05. So when I said negative z of 0.05, it just means this right here. We're now in the left tail. So my critical value is that. So how do we determine whether we reject or not reject? Well, in part 4, the hard part is finding the p-value. because well, it's not hard, but you actually have to do something. Classical, you will know all of these because you can find them on the chart and put them on your formula sheet. But in this one, to find the p-value, you have to actually, look on the chart and look into this. Once we have that, though, no matter what, if the p-value is less than alpha, we reject. And our p-value, 0.04, truly is less than 0.05. That's correct. So we're going to reject the null hypothesis. And over here, we should get the same thing. On a left-tailed test, if my test statistic is less than my critical value, I reject the null hypothesis. And in fact, my test statistic, negative 1.75, is truly less than negative 1.645. So once again, we reject the null hypothesis. So, at a 0.05 significance level, it seems the home is underfeeding the children. If that's the only reason why they could have a lower weight. Or you could just say, at a 0.05 significance level, it seems that the weight of boys at this home are less than the average male child at this age. Any one of those would work for a conclusion. So that's how we do a hypothesis test. Now we're going to look at, so this was doing a left-tailed test. I'm now going to do a right-tailed test. So we're going to do a proportion problem where we're in a right-tailed test. So in a state that does not make wearing a seatbelt mandatory, 14% of drivers wear a seatbelt. A huge campaign was conducted to increase driver seatbelt usage. Now, after the campaign, 104 out of the 590 randomly selected drivers wore their seatbelts. So in order for us to even do a hypothesis test, we have to make sure all the assumptions are met. So first of all, let's calculate our sample proportion, 0.17627. It's a number that goes on. Is n times p and n times p1 minus p, that is, are both of those greater than or equal to 10? Well, that would be 104, which is greater than or equal to 10, and 486 are both greater than or equal to 10. So our condition that our proportion is approximately normally distributed is met, because we got a simple random sample, and n times p and n times 1 minus p are greater than or equal to 10. Our sample sizes are large enough. So we can now say that p hat is normally distributed with a mean of 0.14 and a standard error of 0.14, 1 minus 0.14 divided by the sample size, which is very large, is 590. That's our sampling distribution. So, number one, state the null and alternative. Our proportion is 14. We believe that after this campaign, that proportion should increase. And once again, here's our null hypothesis. Number two, we're going to do this at a 0.5 significance level. 0.5. So alpha equals 0.05. Number three, we're going to calculate our test statistic. So our sample proportion is 0.176. We believe the proportion is 0.14 divided by the standard error. We get a test statistic of 2.52. Now on a right-tailed test, the p-value equals the probability z is greater than our test statistic. That's how we find a p-value for a right-tailed test. So we're trying to find the probability z is greater than 2.52. When we look in our chart and we figure things out, we find out that the p-value is 0.0059. It is tiny. The critical value, as you know, for the right-tailed test is 1.645, because that is, we're looking for the critical value such that 5% is to the right. We know that that's 1.645. So since the p-value is less than alpha, we reject the null hypothesis. Since our test statistic is greater than our critical value, that's the criteria for rejection for a right-tailed test when we do the classical method. Since that's true, since our test statistic is 2.52, and that is definitely greater than 1.645, we reject the null. Both of these should reject the null hypothesis. So at a 0.05 significance level, there is evidence to support the claim the campaign worked to increase seatbelt usage. So that's how we do a right-tailed test. So for the last segment of this video, I'm going to take this and I want to show you how we would use Minitab output. For example, in this problem, how to read this output. So in Minitab, you'd go to Statistics, Basic Statistics, and we want to do a one sample proportion, because we were doing a proportion problem. And I have summarized data. The number of events, well, there were 104 that used seatbelts after that campaign out of a random sample of 590. We're going to perform a hypothesis test where the hypothesis proportion is 0.14, but Minitab doesn't know whether this is a right, left, or two-tailed test, so I have to go into options, and the default is always not equal to, is always a two-tailed test. Well, we're in a right-tailed test, and I want to do my test based on normal distribution. So when I hit OK, I get the output in Minitab. So on a test, I could give you this output, and I could ask you things like, would you reject at a 0.05 significance level? And all you'd have to do is look at this output. You'd look at 0.006 and say, wow, yeah, at a 0.05 significance level, there is sufficient evidence to reject the null hypothesis. I could ask you what the critical value is for a 0.05 test. And so I would leave out the p-value. You wouldn't see the p-value. I would actually not do that part of the output. And I say, based on this Minitab output that doesn't show the p-value, would you reject or not reject? And in that case, I am looking to see if you know how to find the critical value and how to use that critical value as to whether to reject the null hypothesis. So you'd have to know, oh yeah, that's right, the critical value for a 0.05 significance level is 1.645, and this test statistic is way greater than that. So I would reject the null hypothesis. So that Z value that they're talking about here in the Minitab output is your test statistic, the Z naught. And so that's how you would use Minitab output to help you to do hypothesis tests and to make conclusions. Well, thank you very much, and be looking for our third installment where I go into when sigma isn't known. And in that, we're going to learn a whole new bunch of distributions. But don't worry, it's very similar to the standard normal, as you will see. Thanks for watching.